All right. So what we're gonna do here on this slide, on this session, we're gonna talk about the quantitative aspect of chemical change. Okay, get classy. Get classy. All after 2 hours. All right. I'm sorry about that. Quantitative aspect of chemical change. Let's see. So we're gonna start with the content, right? Let's take time. We're gonna relax as much as we can. So we're gonna start with this concept of quantitative aspect of chemical change. So when you talk about a quantitative aspect of chemical change, what are we actually talking about? We are talking about a topic that involves the quantities of the substances. Now, there are many different types of substances that we can talk about. So to make sense out of this, let's talk about medication. We know that we have the pharmacists, we have chemists, we have all of those types of different types of careers, right? So when you talk about people who make medication, for an example, for the pills that we consume each and every day, maybe Grandpa, your Gaviscon, your Panado, your Medlemon, all of those things are made with a certain quantities. What do I mean when I say they're made with certain quantities? For an example, um, we know that a Panado, it is made up of different types of compounds. So those compounds, they came together and they make one medication, which we now call it a Panado. So that Panado, it has, if you take your bottle of Panado, at the back of your Panado, there are ingredients that are found within that medication of Panado. When you take a bottle of Panado, you will see at the back of it, they will tell you you have sugar, this milligrams, you have what syrup, this milligrams. They will tell you all of those things. Those are the quantities that are found within those chemicals. You understand what I'm saying? Even a cold drink or even energy drink, the very same one that we consume, is made up of quantities inside of it. So we are referring to the moles when you talk about the quantities. We are referring to the mass when we're talking about the quantities. We are talking about the number of particles, the number of atoms, all of those things. You understand? So quantitative aspect of chemical change, this topic is all about that. So if you are a person who loves chemistry, so this is your topic. This is the broad topic of chemistry. Okay. So without wasting time, let us start by talking about the definition of a mole. What is a mole? Now we are breaking the topic step by step in small portions. So we're going to learn firstly about mole. So when you talk about the mole, what are we talking about? We are talking about the amount of substance having the same number of particles as they are atoms in 12 grams of carbon 12. Now, again, it's important to know how to define a mole. This is a definition of a mole. Okay, it's important to know how to define a mole. So what we see here on this diagram, it's going to help us much better to understand this definition. So we have a bowl, and inside of this bowl, we have many balls. Now these balls, they actually represent the carbon atom. So carbon atom, it looks like this, right? And therefore, when we take this bowl that has carbon atoms inside of it, we put it on a weighing balance, we get that the mass of these carbon atoms, it is 12 grams. Now, these 12 grams, it is the mass of these carbon atoms. So how many atoms do we have? We can count them, but clearly we cannot count them completely because for sure there are others at the back. So like 1, 2, 3, 4, 5, 6, 7, we can literally count them. So these carbon atoms, they weigh 12 grams. So 12 grams, exactly 12 grams of carbon atom is the same as 1 mole. Because we just literally said, what is a mole? A mole, it is the amount of substance having the same number of particles. These are the number of particles as there are atoms in carbon-12. So these are the atoms of carbon. So if this number of atoms of carbon, they weigh 12 grams. So this is the exactly 1 mole. So there are many different types of atoms that we can talk about, right? From the periodic table. It's not only atom, it's not only carbon. So we can also talk about copper, right? Cu, copper. So if we have copper atoms, right? These are the copper atoms. Here are the copper atoms. So these copper atoms, they weigh 63.5 grams. So this 63.5 grams, it is the same as 1 mole. Even when you talk about your ion, Fe, we need to know 1 mole of Fe is equals to how many grams. So you can understand by just looking at this picture, we are actually talking about the number of moles and we are actually talking about the mass. So the number of moles and mass, they correspond with one another. Depending, hormona, the mass, it's 12 grams and the number of moles there, it's gonna be, it's gonna be 1. So that's the relation between the number of moles and the mass. They have relationship, they have quite hint relationship to one another. That's how we define a mole. So now I want us to look at the relationship between mass, which is what we have just spoke about, the molar mass, and the moles. Now, having a look at this equation over here, N, it represents the number of moles, right? Which is what we have spoke about on the previous slide. And then M represent the mass of our substance. And then capital letter M, it will represent our molar mass, right? So this is the relationship between these two guys over here. Now, this is what you need to understand. According to this equation over here, we said that when we have 1 mole of carbon atoms, that means we have 12 grams of carbon atoms. But now, obvious, when we increase the mass of the carbon atoms, when we increase the mass of carbon atoms, we're going to say 12 multiplied by 2, it will give us 24. So when we have increase in mass of carbon atom, therefore the number of moles will also increase. So that means when we have 12 grams, we're going to have 1 mole. When we have 24 grams of carbon atoms, therefore we're going to have 2 moles. So we can see that the mass, it is actually directly proportional to the number of moles. So this is the relationship between mass and the number of moles, meaning the more we have larger quantity, the more the number of moles increases. So if I were to double this bowel, if I double this bowel, which is 12 grams, it's going to be 24 grams. Therefore, the number of moles will also increase. Therefore, I'm going to have 2 moles when I double this bowel of carbon atoms. So according to this equation over here, we know that when we have something like this, capital letter M, this is N, this is M. These two variables, we say they are directly proportional, meaning when the other one increases, the other one will also increases. They are directly proportional. But when we have something like this, let's say we keep mass as 1, constant, the same, and then here we have the molar mass. Now we have the molar mass over here. So when you talk about the molar mass, what are we actually talking about? When we talk about the molar mass, for an example, of carbon, that's when we're going to use our periodic table. So the molar mass, it is inversely proportional because it is at the bottom. If it was at the top like mass, we're going to say it is directly proportional. But because it is at the bottom of the equation, therefore we're going to say these two variables, the number of moles and the molar mass, we're going to say these two variables, they are inversely proportional. And then these variables, they are directly proportional. So mass is directly proportional to n, right? And capital letter M is inversely proportional. So when we say they are directly proportional, they both, if one increases, the other one increases. But if we say they are inversely proportional, when the other one decreases, the other one increases. They work antagonistically, meaning they work in opposite directions. They oppose each other. If one goes up, the other one goes down. That's inverse proportion. But if other one goes up, the other one goes up. Therefore, that's a direct proportion. Okay, so it's also important to learn the units that we use when we talk about these variables. So the number of moles, the units that we use is just mole. And then the mass, number of the units for mass that we use, we just use the grams. So again, like I said, in physics, mass, we use kilograms in physics. But in chemistry, what we're doing right now, it's chemistry. We use grams. So if they give you quantity in kilograms, make sure that you convert it into grams when we are in chemistry class all the times, okay? So that's why here our mass, it's in grams. And then the units for molar mass, we're gonna have grams per mole. It really does not matter how you represent your per mole. You can also write it like this. You can say grams, okay? Oh, we have a problem right here. Okay, sorry about that. So, okay, so I was here. For molar mass, we use the units grams per mole. Or you can write your per mole like this. You can say grams per mole. Okay, your per can be like this, or it can be to the power of -1 over there. So these are the units for molar mass. Right. So we spoke about the moles, right? Quick recap. We spoke about the moles. We said that the moles correspond with the mass. So the higher the mass, the higher the moles. So the moles, it actually also refers to it also interacts, or it is also related to the number of particles of our atoms, right? So when the mass increases, the number of moles increases. And the equation that we use to calculate the number of moles, it is this one. Do not forget. It's either we use this equation to calculate number of moles or to calculate mass. We cannot use this equation to calculate molar mass. We can only use this equation to calculate the molar mass if we are not told the name of the element that we are working with. Because if we want to get the molar mass, we're going to have to use the periodic table because we are told what is the element. But if the element is not given, we are given the number of moles and we are given the mass, we can calculate the name of the element using this equation. We can calculate the molar mass and get the name of the element using this equation. So normally M, we calculate it using the periodic table, and then this small letter M and mass. So here it's like converting number of moles and mass back and forth. Now let's have a look at these examples. So we're gonna start with example number 1. Okay, let me use don't like this. Right. The system is failing us again. Let's see. Okay. Right. Right. So now here they say to us, calculate the number of moles of each of the following substances. So I'm going to start with number 1A. Number 1A, they want us to calculate the number of moles. So question wants us to calculate N, which is the number of moles, right? We need to calculate the number of moles of each of the following substances. Number 1A, we want to calculate the number of moles of carbon dioxide. So what is given? about carbon dioxide. For carbon dioxide, we are given its mass. They say to us mass for carbon dioxide is going to be 11 grams. So which equation are we going to use to calculate the number of moles? We're going to use the equation that says number of moles is equals to mass divided by the molar mass. I prefer to write my molar mass with double M so that I don't confuse with this one. Okay, it's fine. You can write a capital letter M for molar mass and small letter m for mass. So we want to calculate the number of moles. So this is straightforward. What we're going to do is, on this equation, we're going to substitute the mass that is given in grams. So our mass is going to be 11 grams divided by our molar mass. Do not forget how we calculate for molar mass. Like I said, to get the molar mass, we use the periodic table. So we want to calculate the molar mass for carbon dioxide. So to calculate the molar mass of carbon dioxide, we're going to use these atoms that are involved in carbon dioxide. We have carbon and we have 2 atoms of oxygen. So to calculate the molar mass of carbon dioxide, I'm going to say here I have carbon plus how many oxygen do I have? I have 2. I'm going to multiply those oxygen by 2. Therefore, I quickly run to my periodic table. So when I go to my periodic table, I'm gonna look. I'm gonna look for molar mass for carbon dioxide. I see there it's 12, which is number 6. It's 12, right? And then I go to number 8, and then it's oxygen. My molar mass is 16. Therefore, I quickly run to my problem. So I saw that for carbon, it's going to be 12. Multiply by 2, and then for oxygen, it's going to be 16. And then when I punch everything on my calculator, I'm going to say 12 plus 2 multiply by 16. And then I get 44. So this will be grams per mole. Remember, these units, we use them for molar mass, grams per mole. And then now I'm done calculating my molar mass. I can quickly plug the numerical value over here for molar mass so that I can get my number of moles. Therefore, punching everything on my calculator, when I say 11 divided by 44 to 2 decimal place, already this in 2 decimal place, I have 0.25 mole. And therefore, now I have number of moles for carbon dioxide. That will be number 1A. When we move to number 1B, we need to calculate the number of moles of magnesium carbonate. But they made a mistake here. They were supposed to say calcium carbonate. Okay. It's either magnesium carbonate or calcium carbonate, either way, but we'll use calcium carbonate because this is CaCO3. So for number B again, we want to calculate the number of moles, but we want to calculate the number of moles of what? For calcium carbonate. Oh, it's 3 here. So what is given about calcium carbonate? We are actually given the mass, right? We are given the mass. So mass for calcium carbonate is provided to be 200 grams. So what do we want to calculate once more? Again, the number of moles. So which equation are we going to use? N is equals to mole mass divided by the molar mass. So we can calculate, again, we can calculate molar mass aside, right? We can calculate the molar mass aside, or you can calculate it on this equation, it's fine. But if you want to calculate it aside so that you don't make traffic while you are solving your problem, you can say just next to your question there, you can say the molar mass, just I don't have space this side, I'll utilize this. The molar mass for calcium carbonate, I can see there I have calcium plus I have carbon, I have oxygen. But how many atoms of oxygen do I have? It's O3. I have 3 atoms of oxygen. I'll write my 3 there and O there. And therefore, I quickly run to my periodic table. I'm going to look for calcium We know now what is carbon. We know now what is oxygen. So let's quickly run to our periodic table. Okay, I'm looking for my periodic table. It's somewhere here. There is it. Okay, here's my periodic table. We look for calcium, right? It's number 20. There is our calcium. So atomic mass for calcium, it's 40. So we use atomic mass, right? We use the relative atomic mass to get what? To get the molar mass. So the relative atomic mass for calcium, we saw that it's going to be 40. Plus for carbon, we know that it's 12. Plus 3. For oxygen, it's going to be 16. And therefore, we punch everything on our calculator. We say 40 plus 12 plus 3 multiplied by 16. And then we get 100. Remember, grams per mole. Why do we say grams per mole? Because we were looking for the molar mass. Therefore, we go back to our equation and substitute everything provided because we want the number of moles of our calcium carbonate. The mass is 200 grams. The molar mass is already calculated. There it's 100 grams. Therefore, we divide everything. What is 200 divided by 100? We get 2 moles. Do not forget that you always write your units when you present your final answer. So in this case, N is going to be 2 moles because the units for the number of moles is mole. And then we are done solving this question over here. So how is the session going? Do we understand?
Yes, I understand.
Right. Now let's continue with a content once more again. Now we're going to learn more about the empirical formula. What we did over there on the previous slides, we were converting mass into moles, right? That's what we did. So here we're going to talk about the empirical formula. So now when we talk about the empirical formula, what are we actually talking about? Before we can come to the examples, I want us to define what does empirical formula stands for. It's also important for you to know how to define a term empirical formula for your exam purposes or your test purposes. Now, empirical formula, it is defined as the simplest whole number ratio of elements in a compound. When you have something like this C2H6, it is a compound, right? I don't have to, yes, it is a name. There are many different kinds of compounds. But when you have a look at this compound over here, do we consider it as empirical formula or do we consider it as molecular formula? And why do we consider it as one of the two? So this compound over here, it's true, for sure you guessed it right. We're going to consider it as a molecular formula, not empirical formula. But the question is, why do we consider this compound as molecular formula? It's because this compound, it has ratio of elements with whole numbers, not simplest. These are not simplified. You have 2 goes how many times into 2? It goes 2 times. 2 goes how many times into 6? It goes 3 times, meaning you can simplify this. So now, because this is not simplified, or this is not the simplest whole numbers, so what we're going to do is we're going to have to divide everything by the smallest number. The smallest number between 2 and 6 is going to be 2. So when we divide 2 by 2, we're going to have 1 and CH. And then when we divide 6 by 2, we're going to have 3. Now, what is the name of this compound? It is now called the empirical formula. Why do we call it the empirical formula? Because now it is the simplest whole number ratio. So what is the whole number ratio here? It's going to be 1:3. But what is the ratio of this molecular formula? It's going to be 2:6. So this is not the simplest. So this is the simplest because we simplified it. So the empirical formula is the simplest whole number ratio of elements in a compound. So this is a compound. Now we have the simplified ratio. But here it's a compound. The ratio is not simplified. We're going to have to divide by 2, divide by 2. We're going to have 1:3. Now it is simplified. I hope we get the difference between the empirical and the molecular formula. Now let's have a look or take a look at the examples. Now we're going to do number 2. Example number 2, it says to us, a compound has the following percentage makeup by mass. So we have a compound. We have a compound. So the name of compound it is known because we can see that it's gonna be it is gonna be called KNO. The name of the compound is gonna be called KNO. Like for example, when I come back here, we can have this compound which is CH2O, right? So we know that here, if we didn't know something like this, if we had something like this, here I'll say it's X, then there it's Y, then there it's Z. So I will say my X is equals to 1. My Y is equals to 2. My Z is equals to 1. You get it? So in this case, it is the same similar case. We have X there, we have Y, we have Z. So we're going to have to determine this X and Y and Z so that we can know the exact empirical formula for this. Okay? So let us try to determine this X, Y, and Z. And it's important to know how to write your chemical compound. This can be potassium nitrate, right? Because it starts with K, which is the metal, and then nitrate, which is non-metals and oxygen. Don't write it like KON or OKN or ONK. You're going to get it wrong. You should, as a chemistry student, you're supposed to know how to write the chemical compound using these atoms over here. It's important. All right. Now let us try to solve this question then. So they say to us a compound is the following percentage makeup by mass. When they say by mass, meaning these percentages, they represent mass. So for K, we have 38.61 grams because that percentage, it is the percentage makeup by mass. So that percentage represent mass. Okay? All right. So for K, we have 38.61 grams. And then for oxygen, we're going to have 47.52 grams. For nitrogen, we're going to have 13.86 grams. Now they want us to determine the empirical formula. Like I say, they want us to determine K, X, N, Y, O, Z. We want to determine the empirical formula of this compound. Right? So the question is, how are we going to do that? All the times, you start by determining the number of moles for each and every atom. So let's start. This is given, right? So first step is to answer question number 2. We're going to determine the number of moles for potassium using the equation that we know because we have the mass. So to calculate the number of moles of potassium, we're going to say mass of potassium divided by the molar mass of potassium. And therefore, what is the mass of potassium? The mass of potassium in this case, we have 38.61 grams. Divide by the molar mass of potassium. You're looking for K, right? You quickly run to your periodic table. And we can see that for potassium is going to be 39, which is number 19. 39, K is 39. So we're going to divide this by 39. And therefore, we'll punch that on our calculator. We'll come back. Now, again, we're going to do the same thing for oxygen. We're going to determine the number of moles for oxygen by saying mass of oxygen divided by the molar mass of oxygen. And therefore, we substitute the mass of oxygen is 47.52 grams. 47.52 grams divided by the molar mass of oxygen, it's going to be 16. We'll come back there. Therefore, we calculate the number of moles of nitrogen. We have mass divided by molar mass. It's important for you to start writing the equation before you can do your substitutions all the times. And therefore, the mass for nitrogen, we have 13.86 grams. Divide by molar mass for nitrogen, it's going to be 14. You'll go check it on your periodic table, okay? And therefore, we're going to punch everything on our calculator. So I would like to ask, do you have the answer for number of moles of potassium? If so, what is the answer here? To two decimal places.
0.99.
We have 0.9999 what? Mole. Right?
Moles.
Oh, yes. I thought you said moles. All right. And then for oxygen here, what do we have?
2.97.
2.97 moles. Awesome. And for nitrogen here, how much do we have?
0.99 moles.
0.99 moles. Awesome. Therefore, now we just got the number of moles for each and every element using masses. Now, the next step here, all the times that you need to know, is to do what? Is to take all of this number of moles. So you're going to take the ratio. Ne? We're going to take the ratio. We're going to look at the ratio. Now we're going to look at potassium. We're going to look at nitrogen. We're going to look at oxygen. Now, what is the number of moles for potassium? It's calculated there. It's 0.99. And then for oxygen, what is the number of moles for oxygen? It is also 0.99. And for oxygen, it's going to be 2.97. And what we're going to do, we're going to divide by the smallest number. Always do that. Amongst these numbers, 0.99, 0.99, 2.97, which one is the smallest? Obvious, it's going to be 0.9. So we're going to divide everything by 0.99, divide this by 0.99, divided by 0.99. Here I know I'm going to get 1. Please confirm with your calculation how much am I going to get there. Then here I'm going to get 1 is to 1. Therefore, how much do we get here? 2.97 divided by 0.99.
3.
We get 3, right? So remember, this one is for potassium. This one is for nitrogen. And this 3 is for oxygen. And therefore, I have K1 N1O3. Therefore, this is the final answer, which is the empirical formula of this compound. What is the name of this compound? Potassium nitrate. Okay, so look, I want to show you something. If it was like this, né? Let's round this to 1 decimal places. We have K, N, O. Let's round this to 1 place, to 1 decimal place, to the nearest degree, to the whole number. It's gonna be, okay, let me just leave it like this. Let's say we wrote it like this, K 0.99 and 0.9903. This, it could resemble what? It could resemble the molecular formula. So if you had a molecular formula like this, you're going to have to divide everything by 0.99, 0.99, so that it can take you here, which is now empirical formula. So I just wanted to add that so that you can understand, because I guess that's what we did here. We said, when we have something like this, Here we have the molecular formula, but when we divide by the smallest number, which is 2, it's going to give us the empirical formula. So this also resembles the very same idea that this is molecular formula because it is not simplified, right? Oh, here it's 2, so it's 2,97. This is not simplified, but if we further simplify this in a simplest ratio, now we're going to have the empirical formula. So are we all good? Like, how's everything? Do we understand? Or